All right. So we're happy to welcome this week Stanislaw Soltan. He's coming to us from Poland, working at the University of Warsaw with Adam Bednaritz. And he's finishing up his PhD dissertation, and the topic of his research has to do with quantum measurements, and particularly the quantum Zeno effect and weak values. And he'll be telling us about the work of his PhD dissertation in today's seminar. So welcome, Stanislaw. We're happy to have you here, and take it away.
Thank you very much. Okay, so let's start this way. So yes, the topic of my presentation is weak measurements and quantum Zeno effect. And well, as you said a moment ago, this presentation is based partly on my PhD. Some results are also contained into this paper. It was under review when I did that presentation, so I see that I only put here the archive number, but it is to be published soon. The plan of the presentation looks more or less like this. I start with reminding what the Zeno and also anti-Zeno effect are. I'll discuss briefly the connection with some Legerd-Gard inequality. Then I introduce what I mean by weak measurements in this context and the continuous weak measurements. I'll try to make a brief interlude about modeling with unstable quantum states, and then go back to the topic, so to the Zeno effect under weak measurements. So, as a reminder, if we start with some quantum state, initial quantum state, and we want to check the probability of finding this same quantum state after some evolution, then we observe that for short times that passed, this probability is quadratic in times. So the result of that is basically if we perform one measurement, this is a projective standard measurement, and this resets the system to its initial state, and then wait another short time and perform the measurement again, then we find out that the probability of obtaining two positive results in this manner is greater than the probability of obtaining one positive result with only one measurement after time t1 plus t2. So if we repeat measurements every short time, basically what happens is the so-called Zeno effect, named after a Greek philosopher that argued that the movement is an illusion. It is not possible, but well, the name is sort of a philosophical joke. Indeed, if we take this notion to its extremes, if we go with time between measurements to zero, it is of course not very physical limit, then we obtain what was once called the Zeno paradox, that the system stops its evolution at all, only due to the continuous measurement. But it is such a limit for strong projective measurements is really non-physical. But the actual Zeno effect, the slowdown of evolution for some non-zero but short times between repeated measurements, is definitely physical. And as I mentioned, there is also an anti-Zeno effect. If for some quantum states, quantum systems, if we take short times but not too short, so as to avoid the quantum Zeno effect, we may observe that actually the repeated measurements speed up the evolution. And well, basically one could try to obtain different criteria for whether Zeno effect occur or anti-Zeno effect occur, whether anti-Zeno effect could occur at all in a given system. But all these criteria more or less boils to this first inequality that I wrote a moment ago. So it is the short reminder about the Zeno effect and anti-Zeno effect, and now about some Legerd-Gard inequalities. Oh, sorry for that. Basically, if we look at this, I'm still, okay. If you look at this inequality I wrote here, that is basically the inequality that I intend to discuss during this presentation. It is the Legard-Garg-like inequality. Basically, Legard-Garg inequalities are inequalities that are broken often in quantum mechanics due to the fact that there is no joint probabilistic distribution of measurement results. Basically, if we reformulate this inequality that I wrote a moment ago on a previous slide in the form of expectation values, like if the letter A denotes the result of a measurement, it is either 0 if the system is not in its initial state, or 1 if it is in its initial state, then we should obtain the general inequality of this sort. And obviously it is broken because for short times at least, because projective measurement at T1 is invasive. However, if we try to check this Legard-Garg inequality in a specific experiment that tries to observe the quantum Zeno effect, then we would not observe the breaking of this specific inequality, because the second term here, the expectation value of the observation after time T1 plus T2, assumes that there was no measurement and observation at time T1. So basically, one may ask a question then, can this inequality, this Legard-Garg inequality, be broken in the same experiment that checks Zeno effect? So the story is that we have the Zeno effect, we have the connected inequality, and we want to find if the two can occur in the same experiment. And in order to do this, the right thing would be to reformulate the problem in the context of weak measurements, and I try to motivate this. What do I mean by a weak measurement? Basically, instead of a strong projective measurement at specific times, we have short-living interactions. Here, they are even modeled by delta function in times. Short-living interactions with some probes, with some systems. And during these interactions, the specific observable we want to measure, in this case, it would be a projection on the initial state, is coupled to some degrees of freedom of these probes. There is a continuum limit of this model, which I will discuss in a moment, which makes it a little bit more physical, I guess. Anyway, what happens in this formulation is that we could measure the so-called weak values. Well, the so-called weak values, actually, they are measured in such an experiment because the specific observable is a projection onto initial state, but I get to that in a moment. The weak values were introduced by Taharonov, Albert, and Weidmann, and they are more or less something like that, that we first perform some weak measurement. Weak measurement in the sense as I highlighted before, and I should mention that we go with the coupling strength of the measurement of the measurement apparatus and the specific quantum system to 0. So we perform the weak measurement, and then after some time we perform the post-selection of results based on the fact whether the system, in what state the system was. And the interesting fact about these weak values is that they could, if we treat them as the measurement of the observable A, then they could have the so-called strange weak values, the values that exceeds the range of eigenvalues of the operator A. And as I mentioned, because in our case, the A is a projection, then if we look at the quantity that I wrote here, the 2-point correlation divided by 1-point correlation, then it turns out that if we replace the second weak measurement in such an expression by a single projective measurement, then the results would be exactly the same. And this projective measurement would basically introduce this post-selection of results. So And one more thing to add: strange weak values, these weak values that exceeds the range of eigenvalues, are strictly connected to breaking of the different Legert-Gark inequalities. And so I expect it to be the same in this case. I can spoil some results that I will show later on, that fortunately, this criterion formulated for weak measurements leads us to approximately same criterion for Zeno and anti-Zeno effect as it was formulated in the case of projective measurements, but more on that in a moment. And one more thing to add: there is a sort of a loophole in the whole reasoning, because when we mention Legert inequalities, it should be pointed out that they are fulfilled in some classical case on the assumption that the values of measurements are from some discrete subset, from some finite subset. And in this case, when we discuss the weak values, this assumption is broken. So even though the expectation value of the measurement over different runs is contained in the range of the eigenvalues, it is contained between 0 and 1, the specific outcome of any experiment may exceed this range. And basically, the weaker the measurement, the bigger the noise. So, and the bigger the noise, the worse is this smearing of the possible results around the allowed region. So, if the goal was to observe the breaking of the Legert inequality in this at the same experiment as observing the Zeno effect, then we should add a disclaimer that well, the success depends how much importance we assign to the noise introduced by the measurement. So, to dive a little bit more about the concept of weak measurements, when we perform such weak measurements that at specific times the measurement happens, the evolution operator could be replaced by the specific Krauss operator. This Krauss operator describes the evolution of quantum states provided we measure the specific outcome A, and I chose the Gaussian form of such Krauss operator. Obviously, it could be described as some underlying model of the measurement. And this Gaussian form of Krauss operator has a nice continuous limit. Basically, if we go with the coupling strength of the probes to the system to 0, and with times between measurements to 0, but in such a manner that the ratio of these two things goes to some constant, then we may obtain strictly the Krauss operator for continuous measurement, in which it is a sort of a functional, which argument is a function of describing the measurement results in time. And naturally, we could obtain the density matrix condition and under the condition that we have the specific series of outcomes, and we could obtain the probability of specific series of outcomes. Yeah, and this is more or less the goal of the analysis. We take such an expression and try to discuss, extract something from here. Actually, we could also define the non-selective density matrix if we integrate the specific density matrix that depends on specific outcomes over all possible outcomes. Then we obtain the non-selective density matrix, and it turns out that there is a very simple Rindband-like equation for such a non-selective density matrix, and it will turn out that it is very convenient in an analysis. And as I mentioned, the expectation value in such a model, the expectation value of a measurement at specific time is actually the the value of observable averaged over a state of the system at the beginning. Yeah. So now I'd like to make a short detour to the domain of unstable decaying systems, how they are modeled in my analysis, and well, it may be interesting all in itself. So I start with the Sachin Hamiltonian, which is written here in the second quantization form. So we have some simple two-level system. So its Hamiltonian is denoted expressed by simple Pauli matrices. Actually, I mostly neglected this term in my analysis. We then have some continuum of states, and then we have the coupling between this continuum and the two-level system. So this model, it could be used to describe, let's say, some two-level system interacting with electromagnetic field and being excited, and then de-exciting and emitting a photon. But then we should note that this is the Hamiltonian under the rotating wave approximation. Another idea would be to say that this Hamiltonian is could be applicable as such some model of quantum dot from which an electron can escape to the continuum. And what I actually use for a moment the language that is applicable to the second case, simply because I have some nice pictures taken from there, from somewhere that I are drawn for this particular case. Anyway, there is one nice toy model based on this equation. Basically, if we take the form factor that denotes the coupling between the system and the continuum, such that its square is a Lorentzian. It turns out that such a system is mathematically equivalent to a system in which we have our original quantum dot coupled to some pseudo dot, some intermediate state, which then decays to the continuum, but decays to the continuum with a flat form factor. So we have a relatively simple system compared to the system with some non-flat form factor. We may note also that this is quite general observation. In fact, there is a whole class of such models in which the decaying system is equivalent to a set of some coupled single modes, and then some of these single modes are coupled to some continua by flat form factors. So actually, the analysis of such toy model could be very nicely generalized. The drawback of this particular model is that I assume the energy spectrum is unbounded from below. This is the approximation that makes use of the fact that the tail of this form factor for negative energies is negligible. But if I'd like to generalize it to some thermal theory, then some care must be taken because of that. Anyway, this analysis of some unstable states is what I am doing at the moment. So I also mentioned that there are some nice things that could be found when discussing such systems, more or less related to the subject of quantum Zeno effect, and then I return to Zeno effect. This should be first. One thing definitely connected with quantum Zeno effect is that such models were used to discuss quantum Zeno effect in open quantum systems. In this case, it simply meant the systems without rotating wave approximations. Well, I think that the idea to try the thermal environment would be a good one too. And now, in general, the decaying system with weak measurements seems also like a good thing to investigate. Weak measurements have some interesting properties. The weak measurements that I sketched before, they are non-invasive sort of non-invasive, but at the same time they are not time symmetric and are kind of bad at conservation loss if you have more than 2 measurements. And these things would also be investigated in the context of irreversible quantum decay. So in the context of such models that I presented before. Another thing to mention is that this presentation that I show now is restricted to the so-called direct quantum Zeno effect. I do not discuss the indirect quantum Zeno effect. By that, I mean that the observation is performed directly on the system. I do not discuss the indirect quantum Zeno effect, in which the observation is not done on the system, but on, let's say, the products of decay, or it is not performed on the quantum dot itself, but on the electrons that escaped quantum dots. So, well, some attempt at generalizations may use these simplified models. Anyway, going back to our unstable system, since it could be mathematically transformed in such a form, then, well, the analysis is kind of nice. Let's start with the analysis without the measurement. We have the initial state described by the system, the electron being in the first quantum dot. Or if we do not discuss quantum dot, we have the excited atom. And there are no electrons in this pseudo dot or in the spectrum, in the continuum state. Then the physical state after some time might be written as a superposition of such 3 terms. And then we could try to trace out the continuum, which is fortunately simply because this pseudo dot is coupled to this continuum by a flat form factor. As a result, the solution to this system, after tracing out the continuum, could be split into the pure but unnormalized state and some other state connected with the decay to this continuum. I think, oh, okay. Now I think everything is visible. And where the equations of motions for this unnormalized state are kind of very simple and could be easily solved. So this is a very nice model, as I mentioned. So let's introduce the measurement now. So we should start with the density matrix taken for a specific track of results. The procedure is very similar. We also could mathematically transform the system in such a manner as to have some continuum that could be easily traced out. We have very similar equations of motions for the analogous values as before, only that we have the terms that are connected with the result of the measurement. And now the naive and easy thing, to do to try to discuss the quantum Zeno effect would be to try to put the function describing the results of measurements as 1 for all t. And this approach, well, it is naive because we now face the problem, what exactly is Zeno effect in this context? If it is behavior of the probability of the specific result, a equal 1 for all time, then we have a very nice and simple expression for such a probability. But in fact, we could argue as well that the Zeno effect is the behavior of the actual quantum state under this measurement. So if we say perform a projective measurement after the whole experiment in which we measured weakly the system, then we obtain a different expression. And well, it is not obvious which one is more, so to say, good as a Zeno effect. And as a matter of fact, there is another problem with this approach, that it focuses on a very specific outcome, which when we have weak measurements and like the specific outcome at any time can oscillate little, then to track only these experiments in which we have that specific outcome seems not very convenient. So instead of that, I think that better idea would be to track the expectation value. I mean, expectation value of measurement and in fact other correlations, and use this Lindblad-like equation. So basically, since, as I mentioned before, the weak measurement at the end of experiment could be replaced by a projective measurement, it is more connected with the second case. Like, we perform this weak measurement, we obtain the track of our results, AT, and then we ask if we do the projective measurement at this specific moment that we make a readout, in what state the system would be. One could observe that, well, one observation that one should do immediately is that the state of the system definitely, before the projective measurement, definitely would not be in its initial state. It would be some unpure state. And as a fact, the procedure I outlined above with this weak measurement cannot return the system to its pure initial state at all. Only after we do some additional projective measurement, then we may obtain, well, not only, but if we do some projective measurement, and then we may obtain our initial state back. But what this analysis show is that the direct measurement may solve the imposed decoherence. So it is a little bit related to the concept of the uncollapse that was developed in this work. I found it nice to mention. So let's go to some results of this analysis. First thing first, I slightly redefined the Zeno effect for the purpose of my analysis. So now, instead of tracking the result of measurements through the whole experiments, we are writing the results somewhere, but we are only interested in what happens at the end after, let's say, we do some projective measurement at the end. So we may first ask if this new experiment is related to the quantum Zeno effect at all. And if we do this analysis for repeated projective measurements, then we find that indeed there is some relation. So we have some probability of the series of positive results. This is exponential function. The specific decay rate is taken from the literature. And the tau is, of course, the time between measurements. And if we try to, when I try to perform the same analysis in this case, in which we ignore the results, but still perform the measurements, for some reason, I called it quantum Zeno effect with returns, because, well, the system could, in principle, collapse due to measurement and then go back. But anyway, if we do the same analysis for repeated projective measurements, then we obtain, with some approximations, a very similar result, the same exponents, but modified by some function, hyperbolic cosine. And this small r is rather small compared to the big R. So the correction is not so big. So indeed, these two effects are related, and I think that both could be named Zeno effects with some distinctions, of course. So with that settled, we could go to the continuous weak measurements and obtain the approximate result. This is the result for long times of experiment. And we obtain that there is some decay rate controlled by the strength of the measurement, and we know one may notice that it have a similar form that the case in for repeated projective measurements. We have the integral, we have two overlapping functions, and the function that is introduced by the measurement is peaked. Here it is peaked around 0 because I neglected the energy levels of the system that is decaying. And we can also compare it with Fermi-Golden rule.
Stanislaw, let me ask you a quick question here. Can you
Yes.
go back the slide? Remind us, what is lambda the measurement strength here in the continuous weak measurement case, or what is lambda?
Yes, lambda is the strength of the measurement.
Okay,
yes.
great. Thank you.
And well, the correlations could also be obtained. The correlations which are basically, if they exceed 1, they are instances of decaying aggregate inequality. And we may actually notice that if we draw the values of these correlations for different parameters of the experiment, of the system, and so on and so forth, then we may observe that there are ranges of parameters in which these weak values, actually, because these are those weak values, are strange, are exceeding the range of eigenvalues. And as a matter of fact, we also recover conditions of standard quantum Zeno effect, or at least we have a very similar criterion in this case. So it is nice. Apart from this simple toy model, well, I also tried some other models like square Lorentzian, so it works as well. Of notice is that if we go with one more thing, as it is written here, this approximate result for correlations is obtained for long times t1. So the first results of measurements are read out a long time after the start of the experiment. So after the system left its pure initial state. And if we do the same with the second time also long, then we still obtain that there are some ranges in which these correlations, these weak values are strange, are exceeding 1. So it is a result not only for short times, but should be detectable in some cases for long times as well. This is a specific slice of the previous phase diagram of sorts for a specific value of for a specific value of k0 here in this form factor. And well, there are other things that could be done in this context. One could try to formulate another decayable Legret-Gard inequality. One could notice that these strange values, these weak values, allows to also recover how the form factor more or less looks like if they are measured. And one, of course, could try to estimate some coherence time. Oh, this should be V instead of G. Sorry for this type. And that is all, I think. So in conclusion, Zeno effect is connected with Birknick-Sun classical inequality. We may formulate, of course, the full continuous measurement based on weak measurements. That was presented before. Okay, and I formulated Zeno and anti-Zeno for continuous measurement. Well, this is not the unique formulation. One could try to do something else. For example, one could try to use the framework to try to discuss like the so-called quantum jumps, how the track of the results behaves. Should we expect some sudden changes like going from very close to 1 to 0 or not? But I'm not sure what the result of such analysis would be. And where the experiments detecting Zeno effect may also detect breaking of the classical inequality. with this loophole that I mentioned, that not all assumptions behind the Legge-Gard inequality are fulfilled. And well, that's more or less all. Thank you for your attention.
Okay, thank you very much. Can you go back to your main results? I was interested to hear a little bit more about the connection between the Zeno effect and the Legge-Gard inequality. Yeah, so these sort of contour plots that you were showing.
Sorry, yes. Mm-hmm.
Yes. So tell us again, how is the Zeno effect related to this Legge-Gard, or as we know, the same thing as the weak value? Or what's the connection between those two again here?
The connection is that when the Legge-Gard inequality is broken, then we can observe quantum Zeno effect in some specific experiments, like in projective measurement experiments, and also the sort of quantum Zeno effect in continuous weak measurements. And this follows from the fact that the condition for the Zeno effect could be written in the language of specific probabilities, and these probabilities could be rewritten as some Legge-Gard formulas, which, well, if we would have a classical system, then they would be part of some Legge-Gard inequalities, but since they are calculated for quantum system, they could be broken. And I think this is the connection mainly, that's where we have the criteria for quantum Zeno effect, and these criteria actually are of the form Legge-Gard-like form. I'm not sure if this answers your questions.
Yeah. Can you show us an example of that, or do you have some? Can you point to your plots an example where you see Zeno effect and broken Legge-Gard, for example?
Sure. Actually, I can start with the example taken from the literature that was visible for the moment, I guess, at the beginning. Yes, this is the sort of phase diagram taken from the monography about quantum Zeno effect. And it is done for the similar model that as my toy model, but for the projective measurements, actually. Well, I reproduced this, and this, well, this is the sort, they called it phase diagrams, in fact. On one axis, they had the times between measurements, and on the other axis, they had some parameter describing, characterizing the different systems that they could take into account. In this case, it was the difference between the center of the form factor and the energy of the system. And there is this line of that separates the region of parameters in which we have quantum Zeno effect and the anti-Zeno effect. And the same plot could be reproduced with the condition written above, this written in the form of probabilities, which are actually Legge-Gard inequalities, but in different form, at least for this simple case in which the observability is also a projection measurement. So yes, this is the example, like in this region in which quantum Zeno effect happens, this inequality is broken.
Okay, thank you.
Sorry, actually, this inequality is written for the quantum case. So this is the breaking of this inequality at the moment. Yeah, the classical inequality would have the lower different sign. Okay,
got it. All right, thank you. Other questions or comments from our Zoom audience? Okay, I'll let you think a little bit. Let me, can you go back to your last two or three slides? I want to look more at these contours that you were drawing, Stanislaw.
Sure. Give me a moment. Yeah. These ones?
Okay, yes. So tell us more. So you had this slide. I think we had one more slide. Is that right? Yeah. Tell us more about what these plots mean and what I should take away from them. So,
one thing is that they are kind of similar to the previous ones. So they show the correspondence of the Zeno effect in this case. There is also one more nice thing to take from this, especially from this last one. The region below the curve is, if we look at the scale, is the region in which the weak values have the strange values, like weak values are strange, yeah, and the Legge-Gaert inequality is broken, and so on and so forth. And well, it is, especially in this last case, it may be noted that it can be broken even for some long times. In fact, this phase diagram is made for the one parameter denoting the form factor and for the inverse of the strength of the measurement. So this means that when trying to measure, detect the breaking of these inequalities, we are not restricted to the short times, like when trying to do that in some experiment that would be similar to some standard quantum Zeno effect, so similar to some standard quantum Zeno effect. Another thing is that, well, this is quite a natural consequence, that the value that is 1 over lambda, by the way, the constant Q is introduced here to have have simple numbers, with no specific. They are to scale up this axis. Anyway, that 1 over lambda, that is the strength of the inverse of the strength of the measurement, is somehow related to the similar to the time between measurements in the case of repeated measurements. So it is maybe interpreted as sort of a reaction time of this whole measurement apparatus for the changes in the system. Yeah, I think that these 2-3 things are worth to take as a message home.
Yeah, this reminds me a little bit of this paper you referenced with Nathan Williams about a connection between Legge-Gaert and weak value. We noticed that if you made the measurements longer, effectively you're making stronger measurements, and then for this intermediate measurement, it becomes harder to violate the Legge-Gaert inequality for long measurements. So I think you're seeing the same effect here, if I'm not mistaken.
Yeah, I think it's this.
Okay, good. All right, any other questions or comments?
I have a very quick question. Thank you for the nice talk, first of all. I think I failed to understand whether the results you show, so these contour plots, are they general results or are they restricted to the specific model you're studying, like with these quantum dots and this specific kind of spectral density, or do you observe similar effects when you are studying it?
Yeah, I understand, yes. 2 plots here are taken for this specific form factor, yes, density. Actually, I think that these plots are more exact because this case is kind of simple. I also added one plot for different density. Yes, I think that similar plots could be observed in different cases, but I cannot vouch that the form would be similar. Like we see that in this case, in these two similar cases, the form is kinda similar. In both we have the line that separates the quantum Zeno and anti-Zeno phases, so to say. Yeah, these are for specific, these diagrams are drawn for specific cases. Does it answer your question?
Yeah.
Okay.
All right, good. Other questions or comments? Can you go back to your model about the decaying system? I'm interested in this decaying model.
Naive Zeno. It started here.
Yes, so go to your equations of motion. You went pretty quickly through these equations of motion. I want to take a look at them a little bit. Yeah, okay, so this is good. Yeah, so hold on here. So let's just stop for a second. So what you're doing is you're taking this electron in the left dot, you're tunnel coupling it with a Lorentzian spectrum to some continuum, and you want to figure out what's going on with the quantum state of the dot, okay, after you decay, all right? And so you're only keeping track of the system itself, and so you're going to get decay out of this dot, right? And so that's why your frequencies have an imaginary component, for example. So you're going to have decay. Right? Am I right about that?
Yes, that's true. Yeah, as in particular, the whole continuum is traced out. So this is why this. Yes, I'm not sure if this is what we are referring to.
Yeah, that's right. And so if I look at the solution, for example, so it looks like the solutions take the form, you have alpha and beta there. And so if we look at the decay rate is the imaginary term in the solution. Here. So that's delta. So remind me again, what is capital delta in this model?
A step back, capital delta here is the width of this direction of this total.
Yeah. So this is basically the lifetime. This is the lifetime of the level. So that's
So this is basically the lifetime. Yes.
Yeah,
Sorry for going too fast.
No, it's okay. So this makes sense now. So you have, if you have a Lorentzian spectrum, that delta is basically the inverse decay time. That's how much time it takes to leak out of that thing or of that channel. Indeed, you're seeing that in your solution. So the decay is controlled by delta, and then you have these other plus or minus corrections too. Does anything happen when that square root becomes the argument of the square root passes through 0?
So when okay.
So supposing, for example,
it simplifies calculations. I'm not sure if there is some kind of resonance here. Sorry, you tried to say something and I stopped you.
Yeah, so the thing that's squared is always going to be positive, right? And so, but you could imagine setting E1 to be delta, but I guess gamma is probably a positive parameter in your model. Is that right? Yeah. So it's always going to be real.
Gamma is the coupling. Sorry, going back to this thing. Gamma is here, so it is the coupling strength.
Yeah. Okay, good. All right, so that makes sense. Good. Okay, so then go to your next slide.
Sure.
All right, so then you have these. Okay, now you talked a little bit about this A function, and so is A here is your readout, is that right, or the result of your measurement essentially?
Yes.
Yeah, and so A, I think you took it as so this would be like the occupation of the dot as a function of time, something like that. Is that how you can interpret A?
This is the interpretation, taking into account that this is the weak measurement, so this is not the but
yeah. So your naive solution is basically you just say I'm going to select on the dot being occupied the whole time, right? That's A is equal to 1, right? And so your condition on that. So then these probabilities you write down are conditioned upon the Zeno freezing, essentially. But of course, in reality, if they're weak measurements, you don't know that. You just have some continuous readout that's some noisy readout. So you should condition on some kind of continuous noisy readout, right?
That's true.
Okay.
Yes, that's true.
And so what you want to see here for the Zeno effect is you want the dot to remain in the cavity for longer than if you didn't monitor. That would be somehow a sign of the Zeno effect in this case. Is that what you're looking
That
for?
will be the standard formulation, yes. But then I conclude that it is, well, it may be worth investigating, but I'm not sure if this is very physically feasible to try to discuss such experiments. So instead, I decided to discuss the average over different runs of the experiment and see if there is a relation to the standard Zeno effect.
Yeah, it's interesting because usually the Zeno effect is if you imagine you have a vector and you have a slight rotation of the vector, and it's the fact that there's a projection that's very close to 1 up to something that's like the angle squared, that gives rise to the Zeno effect. What you're talking about here, though, is you're talking about some kind of decay process where you're in the system and you're decaying out. And so I think it's not clear that Zeno projections in this kind of decay model would be able to preserve the occupation of the dot.
You are talking now about this formulation with projective measurements, with strong projective measurements.
For example, suppose I let the system start to decay a little bit, and then project: is the dot, is electron there or not? Do you have the same kind of Zeno effect for this decaying process that you do for a coherent or for a unitary process?
Actually, yes. I think that there is the work. Sorry, I'm going back to the citation. There was the analysis of Atari and Gurvitz about such a system. Gurvitz, sorry.
Yeah, that's fine.
And they concluded that they have a similar model of measurement, I think. They had dot, this electron in the dot could escape, but at the same time, there was some electric current interacting with the dot.
Right.
And so the conclusion is yes, that should be possible in this case. And actually, I feel, yes, in general, in such a cases, one could also expect quantum Zeno effects. I'm not sure if I recall any. Well, I give you the theoretical example of such a conclusion, but I'm not sure if I recall any experimental realization of this type exactly. But the consensus among theorists is that yes. Sorry.
Okay, great. Yeah. So basically the model that you're using is the same as in his Gurvitz paper. Is that right?
Almost the same. Yes.
Yeah, but then you're adapting it to a different question. The question of do you get the Legge-Garg and the Zeno is sort of your main interest. Okay.
Yeah.
Okay, thank you. Any further thoughts or questions from the other Zoom audience? No? Okay.
Yes. So,
wait, go ahead, Tathagate. Yes.
Yeah, I was just wondering how. So you discussed the form of this, I think, transition potential, VE. I was just wondering how one would get that form in practice. Like, does it appear like by itself when you have a system like this, or how do you get that form of VE?
Well, this is a question whether such a form factor is a good approximation of some peak in the actual spectrum actually. This whole model actually could be generalized to discuss like some several peaks in such a thing and so on and so forth. But well, the answer for the question is if the form factor, this function, looks like a peak, then we could see if the Lorentzian is a good fit to it. I'm actually trying to At the moment, I don't have anything about that on the slide, but going back to the beginning of this interlude, I'm actually tried to do something like this. We take some more physical spectrum bounded from below, and we try to perform similar calculations. And it seems that the result is that at some stage of approximations, when I basically, instead of the initial system, I mathematically have a description that involves several single modes. Some of them are decaying to different continuous and so forth. At some stage, I was able to nicely fit some peaks in some form factors with Lorentzians. And in this manner, it seems that one is able to take some more physical spectrum and translate it into such a simplified form, of course, with some approximations. I'm not sure if it answers your question.
Okay, yeah, thank you.
Yeah, usually that kind of spectrum is for a resonant tunneling quantum dot, where you have one resonant level. Yeah. All right, let's thank Stanislaw again for a nice talk.
Thank you.
All right. Goodbye, everyone.
Goodbye. Bye-bye.
Bye. Thank you again.